Hello, everybody, and welcome to video 3 of week 2, where I want to talk to you about what seems like a mundane topic, but is absolutely critically important for us moving forward in the semester. And that is systems of measurement and what we use in astronomy, and then a few special units that we use in astronomy. So let me go ahead and load up my slides, and I'll try to give you some demonstrations throughout the video while keeping this to a reasonable amount of time. So I want to start with what is a scientific measurement? I mean, this is what we do in science is we measure things. And when we use those measurements to test our hypotheses and build theories and an understanding of the natural world around us. So a scientific measurement consists of a quantity or a value, a number, and then a specified unit that goes along with that number. That specified unit is going to be what gives that number meaning. So the unit is actually telling us what is being measured. And if we know what's being measured, that number plus a unit now has scientific value. So you can think about it, the unit is critically important because it gives a number meaning. This is why so many of your science teachers have really emphatically told you over and over and over that you have to include a unit. So the unit is going to tell us what we are measuring, and it might be a length, a mass, a time, force, pressure, something like that. And whenever we're talking about units, we use base units, and then we can add prefixes to those base units. But the base unit is just telling us what we are measuring and what is our basic unit within whatever it is we're measuring. So an example, for distance, we use the base unit of the meter. So 1 meter is a little bit more than 3 feet. So you can see I probably can't put it all on the screen right here, but I have a meter stick. So that is a little over 3 feet, and that is our base unit for distance. For time, we use the second, no surprise there. For mass, we use the gram. For brightness of things, luminosity, we use the watt. So you can think about it like, oh, how bright is that light bulb? It is a 40-watt bulb. It's a 100-watt bulb. For temperature, we use Kelvin. And for frequency, cycles per second, we use the hertz. All of this is really the SI metric system that I'm telling you about, which is sort of the standard for almost all the sciences, and it's what we use in astronomy as well. And I really do want to give you sort of a practical example of why units are so important. So let's take homework number 1. If I were to sit here and tell you, hey, you can get the homework done in 7, you'd be like, whoa, 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 Dr. Lindsay, 7 what? If I said 7 hours, boom, you're out of here. You're dropping this course. It's not worth 7 hours per homework assignment, no matter whether it's a 100 level course or a 400 level course. You're like, that is too long for a single homework assignment. If I said 7 minutes, you'd be like, Dr. Lindsay, I don't know how you did that, but 7 minutes, thank you. I'll knock it out right now and I'll be done with a homework assignment. Wow, just 7 minutes. If I said 7 years, you would probably grab your head, question your reality, look at me and say, that's a PhD dissertation. You better call me doctor after I finish that. As you can see, the unit is critically important. It tells us how much of what we're measuring and what we are measuring, in this case, time. So this is normally where I would go ahead and talk to a slide, but I want to go ahead and try something that I've never really done before. And I want to actually use some new technology that I got and walk you through this so you can take notes along with me. So hopefully this will work without much trouble. Stop share. And share that, please. All right, so sorry that took a little bit longer. This is the first time that I've brought up my whiteboard on my notebook here. So what we're going to do are the prefixes for the metric system. All right, so we're going to have the ones, what we're going to do is we're going to take a unit. Let's use the meter. There we go, I'm finally getting a handle on how to write on this thing. Which the base unit, meter, distance, we use the letter m. So if we wanted to talk about a whole lot of meters all at once, we would use something like the prefix giga. Put a dash to indicate that's a prefix, and we would note that with an uppercase G, and yes, the upper and lowercase does matter. And giga means 1 billion with a B of. So 1 gigameter equals 1, oops, sorry about that, equals 1 billion meters. And in this case, I'll actually write that out as 1 with 9 zeros. So a lot to write out there. I could use scientific notation and say that's 10 to the 9th meters. Then we have mega, it's a prefix. We use the capital letter M, means 1 million of. So 1 megameter equals 1 million meters, which is the same as saying 1, and then we'd have 6 zeros, meters, or we can put that in scientific notation and have 10 to the 6th meters. So you can see it's really easy to just say 1 megameter instead of writing out large numbers like that 1 million meters. And if we're talking about the prefixes that are bigger than 1, we'll have one more. We have kilo. And here we use a lowercase k. And it means 1,000 of something. So when we talk about the kilometer, a distance that you can walk or run easily, 1 kilometer equals 1,000 meters. Or in scientific notation, 10 to the 3rd meters. Not that bad. Okay, so now let's quickly go over the ones that are smaller than 1. So go ahead, if you need to pause it to write all those down, go ahead and pause it. I'm going to erase my screen. And what I'm going to do is now I'm going to do the smaller ones. Now I'm going to go a little bit quicker, so take notes as I go. So we have the ones that are smaller than 1. Let's go with centi. Here I'll always use the square brace to indicate the symbol. So centi means 1/100th of. So 1 centimeter equals 1/100th of a meter equals 0.01 meters equals 10 to the minus 2 meters, however you want to put it. Milli means, and we use a lowercase m, means 1/1000th of something. So 1 millimeter, 1 millimeter equals 1 divided by 1,000 meters equals 0.001 meters equals 10 to the minus 3 meters, a thousandth of a meter. Now we have micro, so we're talking about the micro scale of things, like microtech. Here, your symbol is a little bit different because it's not part of our normal alphabet. It's the lowercase Greek letter mu. And you make a mu, it looks like this. And I'm going to go ahead and you can see I'm going to draw over it. It's like making a U and then turning it into an M. This is 1 millionth of. So 1 micrometer, which we typically call a micron, equals a millionth of a meter. It'll be 10 to the minus 6 meters. And then the smallest one that we'll use in this class is nano, so nanotech, the nanoscale. We use the letter N, and that is 1 billionth. So 1 nanometer is 1 billionth of a meter, which would be 10 to the minus 9 meters. Okay, so I just wanted to go ahead and show those to you to really emphasize that you need to learn what these are. This is going to be something that we have to use for our communication pretty regularly in this class. And now I'm back in my wheelhouse, so I should be able to go back to our presentation pretty quickly, both in the chapter slides and in this presentation. You have this slide, so you can pause and you can look at it. I give examples, but what I want to do is I want to talk about some special special units for distance in astronomy, because the solar system is a big place. We scaled the entire solar system to fit in a football field, and I think we can safely say that most people were kind of astounded by the distances between the planets and the scaled sizes of the planets. So when we're navigating around in the solar system, we want an intuitive unit of distance that helps us make sense of it all. And the unit we use is called the astronomical unit, which is defined as the average distance between the Earth and the Sun. So how far away is the Earth from the Sun? It is 1 astronomical unit, which we will indicate an astronomical unit by saying AU. So 1 astronomical unit, the distance between the Earth and the Sun, is equal to 93 million miles. Or if you want to put a little bit more precise, 149.6 million kilometers, which you're going to remember as 1.5 times 10 to the 8th kilometers. I can't picture 93 million miles in my head, let alone about 150 million kilometers. Like, those numbers just don't make sense. I can't picture that. But what I can picture, and this is really what I was going to show you the usefulness of this unit, is the solar system with the orbits drawn. So if I told you that Jupiter is 5.2 AU away, that makes sense to me, because now I'm like, oh yeah, Jupiter is about 5 times farther away from the Sun on average than the Earth is. But if I told you it's 780 million kilometers away, that doesn't really mean much to me. If I told you that Venus is 0.7 AU away from the Sun, oh, it's about 70% of the distance between away from the Sun than the Earth is. It's closer to the Sun. But if I told you it's 108 million kilometers, that really doesn't mean much to me. So it's really easy to talk about distances in the solar system using the astronomical unit. So if you're in my Astronomy 151 class, the AU is going to be something that you really need to pay attention to. It'll be important for 152 as well, so still make sure you know this. The next one is the light year, a distance, not a time. And it is the distance defined by how far light can travel in 1 year. Light travels at a set speed. It doesn't matter what kind of light it is. In a vacuum, it travels incredibly fast, or at least for the human scale, incredibly slow on the universal scale. And it travels incredibly fast at a speed of about 300,000 kilometers every second. That means it could go around the Earth, around the equator, 7.5 times in 1 second. Light is fast. So we can ask ourselves, given this speed, 300,000 kilometers every second, in 1 year, how long would it take for, or how far would light travel given 1 year. Now, you don't have to do math like this in this class pretty much ever, but I wanted to go ahead and show you. So if I want to know how many kilometers light can travel in 1 year, and I know the speed of light in kilometers every second, I just need to know the number of seconds in a year, which you can crunch that out. 1 year, well, in 1 year, there's 365.25 days. In 1 day, there's 24 hours. In 1 hour, there's 60 minutes. And 1 minute, there's 60 seconds. Multiply, 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 multiply. You get about 3.156 times 10 to the 7 seconds. And that's how many seconds there are in a year. Now, I know that light travels 300,000 kilometers every second. There's this many seconds in the year. Gives me a distance in 1 year. Light will travel 9.46 times 10 to the 12 kilometers. 9.46 trillion kilometers. You can see how big of a number that is right here. I can't picture that in my head. That doesn't have a whole lot of meaning. But thinking about how far light will travel in 1 year does make sense. So the unit, the light year. No, you do not need to remember this calculation. And no, you don't need to remember 1 light year equals 9.46 times 10 to the 12th kilometers. You should know the definition of what a light year is. And then there's this weird unit, which will become important for my Astronomy 152 students, but not so much for my Astronomy 151 students. It is a unit that we use to measure the distances to stars, because by the method that we use to determine the distances to the stars, all the calculations become extraordinarily simple if we use a distance called the parsec. No Han Solo, that's not a time. So the parsec is a distance that just comes out of the way that we measure the distances to the stars. If you're in Astronomy 152, we'll revisit this later with more information about it. But for now, I'll just tell you that the parsec is equal to 3.26 light years. And I want to give you just one real quick summary, just to really hammer in these new distance units. You've probably heard of the metric system before. So the astronomical unit, the AU, is the average distance between the Earth and the Sun. This is very useful for measuring distances in the solar system. The light year, which we label with LY, is the distance light will travel in a time of 1 year. And we use this to measure the distances to stars in distant galaxies, or the size of the Milky Way galaxy, about 100,000 light years across. So it takes light 100,000 years to go from one side of the Milky Way to the other side. The parsec is also used to measure the distances to stars and galaxies, but it is a unit that pops up just out of how we measure distances, what observations we can make at a telescope. And so this is the one when we're doing our calculations based on our telescopic observations, is the unit that pops out quite easily. So normally we measure the distances to the stars in the number of parsecs. And then we have to convert that to number of light years, which makes more sense to the brain. All right, so I hope this was a useful and instructive video for a rather mundane topic. I will see you in the next video. I guess I'm gonna go outside and run 10.